So I would like to start where Joan finished and talk about John, not only about the scientist, which many of you have done, but as Joan said, about his ability to remove the rocks from the way. And that talks a lot about his qualities as a human being. And a great proof of his qualities as a human being is that I can get along with him even though I wear a shirt and long pants. So that proves that he's very flexible and open-minded. On top of that, I must say that, yeah, he removed many rocks that I put on myself, all by myself, during my rough years as a PhD student. He was always caring and always supporting, always there at the right moment, and knowing exactly what to do to help me. So most definitely, thank you, John.
Mention Johan as well.
Oh, of course. I was not directed alone by John, but also by Johan. But after all, Johan is also a creature of your own making. So, so anyway, so I'm here thanks to Johan and to John, and Johan is here thanks to John. So I'm here thanks to John, basically, and. So I'm going to talk about the first author paper I published. So this morning I had two of the co-authors of the paper sitting here among you, and now they left. Those were Fernando Buitrago and Javier Zaragoza Cardiel. So this paper, it's about a massive galaxy without dark matter, which is a first. Now, I should talk about that specific galaxy, and that galaxy is an early type galaxy. So now, for those who are working in stars or the sun, please remember when you were in school, you were learning about the Hubble tuning fork, the Hubble classification. So here we are having the spiral galaxies, but in this talk, I'm going to talk about early type galaxies. So galaxies that are either elliptical or lenticular. So those things are centrally concentrated. They don't have a lot of star formation. They tend to be puffed up. They might have a disk, but they are not as thin as in the case of the late type galaxies. So typically, early type galaxies form in the following way. We first have a phase of wet mergers. So we are accreting several fragments, protogalactic fragments that are gas-rich. So the result of this coalescence of fragments is to form a very compact blue object that is called a blue nugget. So these fragments are merging and are forming this blue nugget, this compact thing, by redshift 2 or 3. And after that, this compact core accretes an envelope. So at the beginning we were having wet mergers, and later on we are having dry mergers. So the wet mergers were creating a compact thing, the batteries of this thing are dying, and later on the dry mergers of satellites that are going around the main body of the galaxy are creating an extended envelope. So I'm repeating myself again, so this is clear. We first form a compact core, and then this compact core acquires an envelope. So the galaxy goes from very compact to much less compact through the acquisition of an envelope of stars through the cannibalization of satellites. Now, there's a very special kind of galaxies which are called relic galaxies that don't undergo the second phase of the evolution. These relic galaxies, they form the compact core, and then nothing else happens to them other than the passive evolution of the stellar populations. There's no more accretion, there's no interaction, nothing. They are the frozen remains of what galaxies were like at redshift 2 or 3. Or shall I say, early type galaxies were at redshift 2 or 3. So these things are extremely rare. And actually, within the local volume, where the local volume is a sphere of 100 megaparsecs in radius, we only know 3 of those things. So now I'm going to talk about one case of such relic galaxies, and this is the prototypical one, the cleanest case of relic galaxy, NGC 1277, which was identified as such back in 2014 by Nacho Trujillo and Ana Ferrer Mateu, among other co-authors. So how do we know that this thing is a frozen remain of what early type galaxies look like at redshift 2 or 3? Well, first we can look at the surface brightness profile. Don't get fooled by the rho here. This is a poor choice by Nacho. It should be a sigma. This is surface brightness as a function of the radius. So if you look at the surface brightness as a function of the radius for this galaxy, NGC 1277, you get here a profile. You don't see the laser anymore. And here you can compare it to that of an elliptical galaxy and a spiral galaxy. Now, if you compare the effective radius of NGC 1277, which is the blue line, we have this blue line here that represents the effective radius of this galaxy. And you can compare it to the effective radius of your regular early type galaxy here in yellow. It's a factor of 5 times more compact than your regular early type galaxy. So NGC 1277 is 5 times more compact than a regular early type galaxy, so it means that it's 100 times denser. So it's compact and dense, but yet it's massive. This thing is a few times 10 to the 11 solar masses in stellar mass, so it's a very massive galaxy. And on top of that, if you check the stellar populations of this galaxy, it has a single stellar population, which is what we expect if this is a relic galaxy that formed at once at high redshift in the early universe. If it had accreted stuff and formed an envelope, we would see different stellar populations corresponding to the accretions episodes and stuff that has been accreted. Okay? And furthermore, we see that this thing is alpha enhanced, which means that the time scale of formation was extremely quick. So all these things are what we expect from a relic galaxy, and this was already discussed in a paper by Trujillo in 2014, and then the spectral analysis, the analysis of the stellar populations was later done by Nacho Martin Navarro and by Ana Ferrer Mateu and others. So now we have this galaxy that we know that it's very special because it's the frozen remain of an early type galaxy at high redshift. So now that we know that this object is very special and almost unique in the local universe, what we need to do is to point at it with all the telescopes we can. So a little bit like if we had a supernova exploding by our side, we would point with all our telescopes because this is a very exceptional event. Well, that's a very exceptional galaxy, so we should all be looking at this galaxy with everything we have. And that's what Nacho did. And what he, among all the instruments he pointed at with this galaxy, is the GCMS, which is a fiber spectrograph at the McDonald Observatory. So here we have the field of view. Here we are having our target, NGC 1277. Here we have NGC 1278, which is a galaxy which is nearby in projection. We don't really know if it's very nearby in reality. Those two things are in a cluster. They are in the Perseus cluster, which is a dense cluster. They have a separation in velocity of about 1,000 kilometers per second, and there's no signs of interaction between these two things, so we don't believe they are very close to each other, but who knows. So here we are having the fibers, and you see NGC 1277, this one here, NGC 1278 here. Now, these observations are very cool because we have integral field data of the galaxy, so we can cover the whole galaxy, but also we have a regular early type galaxy nearby. Now, I have told you that we expect that early type galaxies look like this thing at redshift 2, and this is a regular galaxy that has undergone the full evolution, so has accreted an envelope. So with the same set of data, with the same quality, same scene, same everything, we can compare a regular early type galaxy and an early type galaxy whose evolution has been stopped, frozen in time. So that's very cool, because we don't need to convert data from one instrument to another, and so on and so on. We have exactly the same data, same depth, same quality. And the good thing also is that these are the deepest integral field data that we have for this galaxy so far, so we can extend further out than much more outside than other people that have studied this galaxy. Just to give you an idea on how deep the data go, those were the best integral field data that were available before our work here. And here we have our data at the same, on the top thing, on top we have the same data, but the same data, but with our instrument. I mean, it's the same scale. So at the bottom is the data that were published in the literature, and on the top is our data at the same scale. So we see that we extend much further out, about 50% more in radius, which is critical to find what is the dynamical mass of this thing, infer the dynamical mass of this thing. Now, as you can see, so at the left we have the velocity map. I should stop he's talking about board games. Hopefully he doesn't say anything inconvenient. Anyway, one of my best pals. And the middle we have the velocity dispersion map, okay? And so here we... Okay, let's just shut down the web browser. Okay. Go away.
Turn off the Wi-Fi.
Yeah. Okay. We are setting a board game session at some point, probably next weekend. Well, you probably know more about it than me now. So, velocity map, velocity dispersion for this galaxy. We have the same for NGC 1278. And just to show you the differences between our very compact Rayleigh galaxy 1277 and the regular early type galaxy that appears in the field, here we have the rotation curve of our galaxy to the left, and at the right we have the rotation curve of the regular early type galaxy. So the regular early type galaxy barely rotates. On the other hand, the Rayleigh galaxy is a fast rotator. The Rayleigh galaxy, however, is so compact that it requires, in order to be, it has a huge velocity dispersion in the center of the order of 400 kilometers per second. The other one has much smaller velocity dispersion. The horizontal axis is the same, which is the radius, and you see that the regular early type galaxy is much more extended than the Rayleigh galaxy. Now, if we want to go a little bit beyond that, this very simple analysis, what we need to do is to do a full modeling of the kinematics of this thing. And we did it with Genes and Isotropic Modeling Code by Capellari, who is also a co-author of the paper. And here we go with the modeling. So what we model is this map here. So this map here corresponds to the quadratic sum of the velocities and the velocity dispersions. So here we have the map that we're fitting, and here we're having the fit. And we're fitting a bunch of parameters, but the most relevant one, in the case, well, we have here the inclination of the galaxy, we have here the shape of the velocity ellipsoid, we have here the third one is the mass to light ratio of the stellar component. But what is more important is the fraction of dark matter within 6 kiloparsecs. And why 6 kiloparsecs? Because 6 kiloparsecs is the radius that we are covering with our data. which is 5 effective radii, which is quite a bit for such a compact galaxy. And we find that the fraction of dark matter that we find for this galaxy is less than 5%. At 2 sigma, it's 5%. And it peaks at 0. So, within 6 kiloparsecs of the center of this galaxy, we have at most a 5% of dark matter. And this is compatible with 0. We could have no dark matter. Now, we have another galaxy to compare with, NGC 1278. We do the same trick. And here we have the fraction of dark matter within 6 kiloparsecs. In the case of this galaxy, we go all the way out to 10 kiloparsecs, but we keep the same physical radius for the comparison of the fraction of dark matter. And we find that within 6 kiloparsecs, we are finding 15% of the mass can be attributed to dark matter. Of course, we know the distribution of baryons there because we have stellar mass maps, so they are an input, so what is left is the fraction of dark matter. We are also fitting the black hole, but this is the second order thing. Now, so here comes a complicated plot, and without the pointer, this will be even more complicated. So, in the vertical axis, we are having the cumulative mass within a given radius, okay? And in the horizontal axis, we have the radius. The colors are weird. Those are not the colors that appear in my laptop. Anyway, the line that is dark blue, that is on the top, corresponds to the baryons, okay? I cannot, well, these are the baryons. This is the stellar mass map plus the black hole, if the black hole are baryons. And here in black, you don't see it because it's below the axis, we have the fitted fraction of dark matter. And this gray band here, which, the pointer, this gray band here is 2 sigma of the fitted fraction of dark matter, okay? So if you divide the blue line on the top by the discontinuous line in black here, this is 5%. This is the maximum 5% of dark matter that we're having. On the other hand, the red band represents the prediction of the fraction of dark matter that the galaxy with this stellar mass should have. So we see that there's a mismatch between the predicted dark matter quantity, cumulative quantity for a galaxy of this mass, and the one that we are fitting, which is about here. Okay? Now, if we go to the other galaxy, NGC 1278, the regular ETG galaxy, again, here we have the cumulative mass of the baryons. Here, in black bands, we have the cumulative mass of dark matter, which is the black line here. And in blue and red, we have the expected mass of dark matter from simulations. This is at 2 different redshifts, never mind, the 2 of them are about the same. And we see that the predicted dark matter fraction is perfectly compatible with the one that is fitted. So the blue line and the light blue line and the black line are almost on top of each other, and especially if you take into account the 2 sigma uncertainties, they are most certainly on top of each other. So, in NGC 1277, we are finding that the galaxy has no dark matter, which is at odds with expectations for a galaxy that has that stellar mass. And in the case of NGC 1278, we are finding a fraction of dark matter that is perfectly compatible with what is expected from simulations. Let's see that in another plot. So in the top plot, in the horizontal axis, we are having the stellar mass of the galaxy, and in the vertical axis we are having the dark matter fraction within 5 effective radii. So in the case of NGC 1277, 6 kiloparsecs corresponds to 5 effective radii, and for 5 effective radii we have a dark matter fraction that is compatible with 0 and up to 5%. On the other hand, for 5 effective radii, we are expecting from simulations that the fraction of dark matter that we are finding should be about 60%. So we see a discrepancy of many sigma between what we are finding and what would be expected in models. Now you can tell me, well, hold on, you're cheating a little bit here, because this galaxy is extremely compact. So maybe the relevant scale here is not the scale, the size of the galaxy in effective radii. Maybe you should take a physical scale here. So instead of looking at a given number of effective radii, you should look at a given number of kiloparsecs. And that's what we are doing in the lower plot. So in the lower plot, again, in the horizontal axis, we are having the stellar mass, and in the vertical axis, I'm showing the fraction of dark matter within a radius of 6 kiloparsecs. So again, we have a tension between this point and the expectation. There should be another band here. So this is the 1 sigma band. Here we should have this 2 sigma band, but I don't know what happened to the colors. The projector is doing strange things, I think. But it has disappeared. But again, there's an incompatibility between this point and the bands here. On the other hand, for NGC 1278, the regular early type galaxy, we are finding that the fitted dark matter fraction is perfectly compatible with the expectations from the simulations. So we can say that as it stands now, NGC 1277 is poor in dark matter compared to other early type galaxies. Yeah, no, it's not in my screen. But anyways, now it's purple. That's right, because you see, it should be purple, and now it's blue in color. I don't know what's going on with the colors. Well, anyways, just 3 slides left. So why the fact that this galaxy is poor in dark matter explains naturally why this galaxy is a relic. Because if you have not accreted your envelope of dark matter, you shut down dynamical friction. And if you shut down dynamical friction, all satellites that come nearby the galaxy undergo a parabolic flyby and don't come back. If you had a dark matter halo, you would have dynamical friction, an incoming galaxy would spiral in and be accreted. So if you don't have dark matter, you explain naturally why this galaxy is a relic. Now the question is, why is the galaxy lacking dark matter? And we have no idea. That's something that theoreticians should answer. But I will do a little bit of hand-wavy stuff, which is what I have been doing because the pointer is not working anyway. So 2 possibilities that I have been finding in the literature. One is that when you are in a dense environment, like the Perseus cluster of this thing, there's a certain amount of material that is stripped away as the galaxy goes around the cluster. So in this plot, we are having the look-back time, and here we are having the mass of different components, and in blue you have the stars, and in gray you have the dark matter. And you will see that the gray line goes down with time, so that means that some of the dark matter is being stripped away. Now, most of the dark matter that is being stripped away is from the outskirts of the galaxy, but in our case we want the dark matter from the inner parts of the galaxy to be stripped away. So this is a little bit more challenging to explain, but in a recent paper by Moreno et al. 2022, they argue that dark matter is in much more elliptical orbits than stars, which are much more circular orbits. So when they are in their apocenter, it's sort of easy to remove the dark matter compared to the stars. But this is a little bit hand-wavy, qualitative, and Moreno was looking at dwarf galaxies in the potential of the Milky Way or Milky Way-like galaxies. So it might or might not work in the case of NGC 1277. The other possibility, and is the one that I prefer, but the second author of the paper, Nacho Trujillo, would disagree, is that of a bullet cluster-like event. Now imagine that early in the life of the galaxy, you're forming the galaxy by merging a few gas-rich fragments. So those gas-rich fragments When they collide, the gas stays in the middle, just like in the bullet cluster. The gas stays in the middle, but we are talking about gas that is much denser and much cooler than that, much denser than that in the bullet cluster. Orders of magnitude denser. So it cools down fast and it forms stars. If the relative velocity of the fragments that are merging is large enough, the dark matter might escape the system and never come back. In order for that scenario to work, you need a relative velocity of about 2,000 kilometers per second. And the fastest moving galaxies in clusters have relative velocities of about 2,000 kilometers per second. So that would be marginally compatible with the evidence that we are having. And Johan is looking at the clock, so I will conclude here. Thank you for your attention.